previous lectures, we have discussed equation of state of real gases, principle of continuity of state, and after that we derived Maxwell's distribution of molecular speeds. In previous lecture, we have discussed Redlich-Kwong equation, that is P is equal RT by Vm minus B minus A by Vm, Vm plus B into T to the power 1 by 2 is equal RT. Then we discussed Birth-law equation, that is P is equal RT by Vm minus B minus A by T Vm square. After that, we discussed Redlich equation, that is P is equal RTE to the power A by RTVm by Vm minus B. Then Gaseous equation, that is P plus A by T Vm plus C whole square into Vm minus B is equal RT. And then we discussed virial equation of state, that is P is equal RT by Vm into 1 plus Bt by Vm plus Ct by Vm square plus dt by Vm cube plus dash dash. And then we discussed the principle of continuity of state, which states that a liquid near the critical point is just a highly compressed gas. After that, we derived Maxwell distribution equation for molecular velocity, that is dNc by n is equal 4 pi m by 2 pi kt to the power 3 by 2 into c square e to the power minus mc square by 2 kt into dc. Here dNc is number of molecules having velocities between c and c plus dc, and n here it is the total number of molecules. M is the mass of the molecule here, T is absolute temperature, and K is the Boltzmann constant. Now, in this lecture, we will discuss effect of temperature on molecular speeds. Then we will derive most probable velocity, then root mean square velocity, and after that we will derive average velocity. Let us start with effect of temperature on molecular speeds. The Maxwell distribution equation is dNc by n is equal 4 pi m by 2 pi kt to the power 3 by 2 into c square e to the power minus mc square by 2 kt into dc. So, the distribution of molecular speed is 1 by n into dn by dc. This quantity is plotted as ordinate against various values of c, that is molecular speed. So, it is clear from this graph the fraction of the molecules with too low and too high velocities is very small. It is visible from this plot here, and the fraction of the molecules having speeds greater than 0 goes on increasing with increasing velocity, passes through a maximum and then again falls towards the high velocities. There is a certain velocity for which the fraction of molecules is maximum. We will call this most probable velocities. By increasing the temperature, the shape of the distribution curve remains unchanged, but flattening of maximum takes place, which occurs at high velocity if the temperature is raised. So, we observed here that on increasing the temperature, the entire distribution curve shifts to the right, and the fraction of molecules having high velocities increases with increase in temperature, and this effect is mainly due to the presence of the exponential term which increases rapidly with increasing temperature. In the Maxwell distribution equation, the Boltzmann factor, that is e to the power minus mc square by 2 kT, increases with temperature, as the exponent has a negative sign and temperature T appears in the denominator. Now, let us start the types of molecular velocities. There are 3 types of molecular velocities. First one is most probable velocities, then average velocities and root mean square velocity. Let us start with average velocity. It is represented by VAVG or CAVG. The average velocity, it is given by the arithmetic mean of the different velocities possessed by the molecules of the gas at a given temperature. Now, let us start the derivation of average velocity. If C1, C2, C3 so on are the velocities of N1, N2, N3 so on number of molecules respectively, then the average velocity is C1 plus C2 plus C3 so on to Cn by total number of molecules, that is n. So, we will write it as C average is equal 1 by n summation Ci. Now, we can write it as C average is equal 1 by n integration 0 to infinity summation dn. The summation of different velocities is replaced here by integration. Why? Because all types of velocities ranging from 0 to infinity are involved here. So, the equation is now C average is equal integration 0 to infinity C dnc by dn. As we know, the value of dnc by n, the number of fraction of molecule is given by Maxwell equation, that is dnc by n is equal 4 pi m by 2 pi kT to the power 3 by 2 c square into e to the power minus mc square by 2 kT into dc. Now, we will substitute this value in our equation of C average. So, now the equation is C average is equal integration 0 to infinity 4 pi m by 2 pi kT to the power 3 by 2 into C square C into C to the power minus mc square by 2 kT into dc. So, now the equation is written as C average is equal integration 0 to infinity 4 pi m by 2 pi kT to the power 3 by 2 integration 0 to infinity. Here C cube into e to the power minus mc square by 2 kT into dc. Let the term m by 2 kT is A. So, we get C average is equal integration 0 to infinity 4 pi m by 2 pi kT to the power 3 by 2 integration 0 to infinity C cube e to the power minus a c square into dc. Since from calculus integration 0 to infinity c cube e to the power minus c square into dc is equal 1 by 2. So, we get integration 0 to infinity c cube e to the power minus a c square into dc is equal 1 by 2a square. So, now we will substitute this value in our equation. We get C average is equal integration 0 to infinity 4 pi m by 2 pi kt to the power 3 by 2 into 1 by 2a square. As we know that a is m by 2 kt here. So, we will substitute the value of a, then we get C average is equal 4 pi m by 2 pi kt to the power 3 by 2 into 1 by 2 m by 2 kt whole square. Now, the equation is C average is equal 4 pi m by 2 pi kt whole 3 by 2 into 2 kt by m whole square into 1 by 2. The equation is now C average is equal 4 pi m by 2 pi kt to the power 3 by 2 into 4 k square t square by 2 m square. On solving the above equation, we get the average velocity. So, the average velocity is root 8 kt by pi m. As we know, the Boltzmann constant is ideal gas constant by Avogadro's number. So, by putting this value, we get C average is equal root 8 RT by pi n naught into m. As we know that Avogadro's number is equal molar mass by molecular weight. By using average velocity, we can calculate the molar mass of this gas by using this equation. C average is equal root 8 RT by pi m. As we know, the ideal gas equation is PV is equal RT. So, in place of RT, if we write PV, that equation is then C average is equal root 8 PV by pi m. As we know that density is equal m by V. So, we can write C average is equal root 8 P by pi into D. So, C average is equal 1.6 into root RT by m. Let us discuss most probable velocity. It is represented by VMP or CMP. Most probable velocity is defined as the velocity possessed by maximum number of molecules of a gas at a given temperature. The Maxwell's distribution equation is dNc by n is equal 4 pi m by 2 pi kt to the power 3 by 2 into c square e to the power minus mc square by 2 kt into dc. So, by differentiating the right hand side of this equation with respect to c and then equating the result to 0, condition for maxima and minima in the distribution curve, we get dNc by n is equal 4 pi m by 2 pi kt to the power 3 by 2 into c square e to the power minus mc square by 2 kt into dc is equal 0, or d by dc is equal 4 pi m by 2 pi kt to the power 3 by 2 into c square e to the power minus mc square by 2 kt is equal 0. We get 4 pi into m by 2 pi kt to the power 3 by 2 into 2c into e to the power minus mc square by 2 kt into 1 minus mc square by 2 kt is equal 0. So, the term is a constant here and this cannot be 0. this term is 4 pi m by 2 pi kt to the power 3 by 2. So, hence 2c into e to the power minus mc square by 2 kt into 1 minus mc square by 2 kt is equal 0. So, there are 3 possibilities now, that is, first one c is 0, second is e to the power minus mc square by 2 kt is 0, and it is possible when c is infinity, and third possibility is 1 minus mc square by kt is 0. The first two possibilities corresponds to maxima or minima when c is 0 or c is infinity. These are not possible. Since no molecule have velocity equal to 0 or infinity, so the other solution is obtained by putting the quantity 1 minus mc square by 2 kt, that is third possibility, that is equal to 0. So, the term 1 minus mc square by 2 kt is equal 0. Therefore, c square is equal to kt by m. This is most probable velocity. So, most probable velocity is cmp is equal root 2 kt by m. As we know that Boltzmann constant is equal r by n. So, we can write cmp as root 2 rt by n into m, as Avogadro's number is m by m, that is molar mass by molecular weight. So, we can write cmp as root 2 rt by capital M. Ideal gas equation is PV is equal RT. So, we can write PV here in place of RT. So, CMP is equal root 2 PV by M. As we know that density is equal mass by volume. So, we can write the CMP as root 2 P by D. So, most probable velocity is 1.4 root RT by M. Let us discuss root mean square velocity. Root mean square velocity is represented by CRMS symbol, and root mean square velocity is defined as the square root of the mean of the squares of the different velocities possessed by the gas molecule at a given temperature. So, CRMS is equal C square whole 1 by 2 is equal C1 square plus C2 square plus C3 square, so on Cn square by n whole 1 by 2. So, we can write it as CRMS is equal 1 by n summation I Ci square whole 1 by 2, or CRMS is equal integration 0 to infinity C square into dNc by n whole 1 by 2. For fraction of molecules from Maxwell equation, we will write as dNc by n is equal 4 pi m by 2 pi kt to the power 3 by 2 into c square e to the power minus mc square by 2 kt into dc. Now, we will substitute this value of dNc by n in our equation. The equation becomes CRMS is equal 4 pi m by 2 pi kt to the power 3 by 2 integration 0 to infinity c to the power 4 e to the power minus mc square by 2 kt into dc whole equation to the power 1 by 2. So, let the term A is m by 2 kt in the equation. So, now the equation is CRMS is equal 4 pi m by 2 pi kT to the power 3 by 2 integration 0 to infinity C4 e to the power minus AC square into dc whole power 1 by 2. Since by calculus integration 0 to infinity C4 e to the power minus AC square into dc is equal 3 root pi by 8a to the power 5 by 2. Now, by substituting the values of C4 and dc in equation, we get CRMS is equal 4 pi m by 2 pi kT to the power 3 by 2 into 3 root pi by 8a to the power 5 by 2 whole to the power 1 by 2. Since m by 2 kT is a here, so we will put this value and we get CRMS is equal 4 pi m by 2 pi kT to the power 3 by 2 into 3 root pi by 8 m by 2 kT to the power 5 by 2 whole 1 by 2. CRMS is equal 4 pi m by 2 pi kT to the power 3 by 2 into 3 root pi by 8 into 2 kT by m to the power 5 by 2 whole to the power 1 by 2. On solving this equation, we get the value of root mean square velocity, that is CRMS is equal root 3 kT by m. As we know, the Boltzmann constant is equal ideal gas constant by Avogadro's number. So, in that term CRMS can be written as root 3 RT by n into m. Avogadro's number is equal m by molecular weight, that is CRMS is now root 3 RT by m. As we know, the ideal gas equation is PV is equal RT. So, in place of RT, if we put PV, now the equation for root mean square velocity is equal root 3 PV by m. Density is equal mass by volume. So, now we can write this equation as CRMS is equal root 3 P by D. The value of root 3 is 1.7. So, now we can write the CRMS is equal 1.7 into root RT by m. Let us discuss the relation between root mean square velocity, average velocity and most probable velocity. Root mean square velocity is root 3 kT by m, average velocity is root 8 kT by pi m, most probable velocity is root 2 kT by m. So, that is root 3 ratio root 8 by pi and this is root 2. The value of root 3 is 1.732 and this is 1.595 and the value of root 2 is 1.414. So, the relation between them, that 1 root mean square velocity is equal 0.92 average velocity or 0.82 most probable velocity. Now, I have a numerical problem for you. Just calculate the average velocity for oxygen molecule at 298 Kelvin. The solution is, as you know, the C average is equal root 8 kT by pi m, or you can write it as root 8 RT by pi m. The ideal gas constant R is 8.314 joule per Kelvin per mole and the value of temperature is given it is 298 Kelvin. The molecular mass m of oxygen is 32 into 10 to the power minus 3 kg per mole. Now, if you calculate this value by putting this value in equation root 8 RT by pi m, you get C average is equal root 8 into 8.314 into 298 by 3.14 into 32 into 10 to the power minus 3. So, when you calculate this value, you get the C average for oxygen molecule at 298 Kelvin is 444.14 meter per second. I have another problem for you. Just calculate the root mean square velocity for a gas having density 1.2504 kg per meter cube at 0 degree centigrade temperature and a pressure of 1 atmosphere. So, the solution is here. The root mean square velocity is root 3 kT by m, or in terms of density you can write it as root 3 p by d. The value of pressure is given in this numerical, that is 1 atmosphere. So, we will convert this value in Newton per meter square. So, 1 atmosphere is equal 101,325 Newton per meter square. The density is again given in numerical problem, that is 1.2504 kg per meter cube. Now, CRMS is equal root 3 p by d. We will put the values in this equation. So, we get CRMS is equal root 3 into 101,325 by 1.2504. So, when you calculate this value, you will get CRMS is equal 493.05 meter per second. So, viewers, in this lecture we have discussed 3 different types of molecular velocities. First one, the most probable velocity, and we derivate it. We got CMP is equal root 2 kT by m. Then we derived root mean square velocity. It is CRMS is equal root 3 kT by m. And average velocity, it comes C average is equal root 8 kT by pi m. Then we discuss the derivation and comparison between these 3 molecular velocities. So, in the next lecture series of gaseous state, we will discuss some collision properties of gaseous state like collision diameter, collision frequency we will discuss, and after that we will discuss and derive free mean path.